Hi students, how is everyone doing? So yes, good afternoon. So today we are going to be covering 3 small topics, fairly easy. Just again, like always, we have to understand everything very logically, nothing to memorize. Yes, it helps to memorize the formulas, but it definitely helps more when you understand how you're getting the formulas, because there might be exceptions to that formulas, and the only way to actually get the right answer is by knowing where the formulas are coming from, right? How to derive those formulas, how did we come up with the formula. So just like that, we are going to be covering 3 topics today. The first is sum of all possible numbers using given digits. Then we will see exponent of prime in any big number. How do we calculate that? And finally, we are going to see, as the title says, select non-consecutive objects. So earlier we learned how to arrange the objects in such a way that certain objects are never adjacent to each other. We were arranging. Today we are going to learn how to select non-consecutive objects. We cannot select any 2 adjacent objects. So alright, let's begin. Yes, this is entirely in English. Okay, so let's start. The first topic is sum of all possible numbers. In one of the first classes, we saw how to calculate the total possible numbers using the given digits, right? For example, this simple problem, find the, let's forget the sum for a bit, all the 3-digit numbers that can be formed using 1, 2 and 3 without repetition. So how many options, how many possible numbers do we have? 3 factorial, so 6, right? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. These are all the possible numbers we can get using 1, 2 and 3 without repetition, all the 3-digit numbers, right? Now we have to add these. Now we have to add all of these. So if you look at this, there are in each column 2 1s, 2 2s and 2 3s, right? In each column we have exactly 2 1s, 2 2s, 2 3s. That means total 6 possibilities for each column, right? So what does this sum up to? 2 into 1 plus 2 into 2 plus 2 into 3, that is 12. If you take 2 common, this becomes 2 into 1 plus 2 plus 3, so we get 12, right, for each column. That means if we add this, we get 12 and 1 is carried over, then 12 plus 1 13 plus 1, then 12 plus 1 13. So this is our final answer. Of course, like always, we cannot list all the possible numbers directly. We need to be smart about it. So let's break it down. How did we reach 1332? We had 12. We just had to multiply it by 111, right? 12 into 1 plus 12 into 10 plus 12 into 100. For each column, for each digit, we had to do this, right? Now where did we get this 12 from? We got it from 2 into 1 plus 2 plus 3 into 1 plus 10 plus 100. So we know 1 plus 10 plus 100 is because we have a 3-digit number. So we went from 1's digit to 100's digit. We have 1 plus 2 plus 3 because these are the 3 digits that are given to us. What is this 2? 2 is, for each digit, how many possibilities are there? If we fix this one digit for this one, how many possible numbers can we make? 3 minus 1, 2 factorial, right? For each digit we can have 2 factorial numbers, right? We fix one digit anywhere and we get n minus 1 factorial numbers for that digit. So that means this becomes n minus 1 factorial into sum of all digits into 1 plus 10 plus 100 up to 10 raised to power n minus 1. Right, because we're starting from 10 raised to power 0, then 10 raised to power 1, 10 raised to power 2, up to 10 raised to power n minus 1. And this is the formula that we get. So if it is a straightforward question where we have all distinct digits, right, and we can form n factorial numbers here, then we will just calculate this way. N minus 1 factorial, because for each digit we have n minus 1 factorial options. You can also look at it this way, that the total numbers are n factorial. How many digits are there? N digits. So for each digit we get n factorial divided by n, right? Which is n minus 1 factorial. So you can look at it any way, it's the same thing. N minus 1 factorial for each digit multiplied by sum of digits multiplied by 1 plus 10 plus 100 up to 10 raised to power n minus 1, right? Depending on how many digits we have in the number. Clear? Now, find the sum of all 4-digit numbers that can be formed using the digits 1, 2, 3 and 4 without repetition. Same as before, we can directly apply the formula here because the digits are distinct, the number of digits is 4 and we can have 4 factorial numbers here. So, 4 minus 1 factorial into sum of all digits into 1 plus 10 plus 100 plus 1000, or you can directly write 1111 for each digit. Alright, so this is 3 factorial into 10 into 1111, that is 60 into this, which is this. Okay. But what if now there's a slight variation? Now we have to form 3-digit numbers using 1, 2, 3 and 4. How many such possibilities are there? We first select which 3 digits to take, 4C3, and then we arrange them. So 4 into 3 factorial 24, or you can look at it this way, that we have to fill these 3 spaces, 4 options for this, 3 options for this, 2 options for this. So 4 into 3 into 2, 24. Right, simple. Now, but now we have to find the sum of all digits, right? So let's assume we have the 3 digits. We have selected which 3 we are going to take and which one we are going to leave, right? We can leave 1, we can leave 2, we can leave 3, or we can leave 4. We have 4 options. We will either skip 1, or we can skip 2, or we can skip 3, or we can skip 4 and take the remaining 3. Now, let's say for example, right now I have chosen which 3 digits I am going to take. Let's say it is 1, 2 and 4. Now for this case, I will take the entire sum as number of digits. So it's my previous question, right? The 3-digit numbers using these 3 digits. 3 minus 1 factorial into 1 plus 2 plus 4 into 1, 1, 1. Right? Now let's call this S3 because we left 3. Right? So this becomes 2 into S3 into 1, 1, 1. S3 because we skipped 3. Just like that, we are going to have 4 sums. 2 into S1 into 1, 1, 1. 2 into S2 and 2 into S4, 1, 1, 1. Right? Now, what is the sum of S1 plus S2 plus S3 plus S4? If S is the total sum, alright? If S is 1 plus 2 plus 3 plus 4, then S1 is S minus 1, S2 is S minus 2 and so on. So, S1 plus S2 plus S3 plus S4 becomes 4 times S minus 1 minus 2 minus 3 minus 4, which is again S. Right? S1 is S minus 1, S2 is S minus 2. So, we will add all of these. 4S minus so finally that is 3S. So, taking 2 and 1, 1, 1 common out of this, we get 2 into 3 into sum of digits into 1, 1, 1. So, 60 into 1, 1, 1, that is 6660. Okay? But if you, no, it is not recording. If you think that these are very easy questions for you, that's amazing. I'm very happy for you. I'm very proud of you that you have such a great prep already. You find this very easy. But whenever we are studying, whenever we are learning a new topic, then we have to start from the basics because that is where we get the best understanding. Okay? So do not worry. This course is going to cover all the questions. In the end, we are going to have as many sessions as it takes to just practice difficult questions. Trust me, we are going to get there. And then I know you all will be complaining, ma'am, this is too hard, ma'am, this is too confusing. We will do it, okay? We will understand everything there as well. But in order to do that, we have to understand every formula, where it's coming from, how we can get to the answer every single time, okay? Yes. So, if you see, this is similar to the previous question, 60 into, except the number that we were multiplying it was 1111 because it was a 4-digit number, and in this case it's a 3-digit number, so 111. Do not memorize, just understand logically how we can do it. Now, what if one of the digits was 0? We have to form 4-digit numbers. So 0, 1, 2, 3. Now how many numbers can we make? Forget about the sum for a second. And how many 4-digit numbers can we make? Come on, quick, quick, quick. No, not 7. Come on, you can do this. Especially the students who were complaining that this was an easy question. Come on. What is the total number of numbers that we can make? Three into 3 into 2 into 1. Thank you. So we have 3 options for this. 3 options for this, 2 options for this, 1 option for this. So this is 3 into 3 into 2 into 1, 18. Or we can look at it that we have 4 factorial, we arrange all of them and we exclude the numbers where 0 was in the leftmost place. So how many such numbers? We fix 0 and then we have 3 factorial. So 4 factorial minus 3 factorial, that is 18 again. Of course, we will get the right answer if the method is correct. So you can take a look at both the methods. You should understand both the methods, because in this question we are going to use this one. Why? Let's see. We need to find the sum of all 4-digit numbers that can be found using 0, 1, 2 and 3. The only condition is, in order for this to be a 4-digit number, 0 cannot be here. So let's first find the sum the old way. Let's assume 0 can be here. Okay? So the total will be 4 minus 1 factorial into sum of all digits 0 plus 1 plus 2 plus 3 into 1, 1, 1. This is the total. Now this is also including which numbers where 0 is in the leftmost position. Let's subtract the sum of all such numbers. So once we fix 0 here, what do we get? We have all the 3-digit numbers using 1, 2 and 3. Right, that's the sum of all such numbers. So that will be 3 minus 1 factorial into 1 plus 2 plus 3 into 1, 1, 1. And here you go. That's your final answer. If you want to calculate 3 factorial, that is 6 into 6 into 1, 1, 1, 1 minus 2 into 6 into 1, 1, 1. So we take 12 common. From here we are left with 3, 3, 3, 3 minus 1, 1, 1. That is 12 into 3, 2, 2, 2. So whatever you get here. Okay? So this is how you can approach the problem very easily. These are just two simple problems, and then we take all possible cases and we remove the cases that we do not want. Just make sure that you're removing the sum and not just the cases. Just focus on your studies, bache. It's okay. You will have some students who are not here to study. That's okay. Just understand what is going on here. Reply with the answer in the chat. I'll look at your answer. Okay. So clear? This is how we can take care of such cases. Let's see another case. Find the sum of all 4-digit numbers that can be formed using 1, 1, 2 and 3. Let's go back to our how many numbers can we make using these 4 digits. We arrange all of these and we divide it by the repetition number. So this comes out to be 24 by 2, 12. Right? We have to find the sum of all these 12 numbers. So we are going to use the similar approach. I suggest you look at this in general. If you're struggling to find the sum, if you can't think in the beginning, how to find the sum of all such numbers, then take this approach. Find the number of numbers that can be there, see how we were calculating, and then find an idea on how we can use the same thing to calculate the sum. For example, here we take the entire sum. The entire sum is 4 minus 1 factorial into 1 plus 1 plus 2 plus 3 into 1, 1, 1, 1. This is the entire sum. But we are counting each case 2 factorial times. That is why we divided the entire thing by 2 factorial, right? Because we were counting every number 2 factorial times, or 2 times, or twice. So that means even the sum will be double what we wanted. So we will just divide it by 2 factorial. And finally we have 3 factorial 6, 1 plus 1 plus 2 plus 3, 7 into 1, 1, 1, 1 by 2. So this comes out to be 21 into 1, 1, 1, 1, that is Perfect. Right? Easy? So this is how we can apply the same thing in various situations. Just understand how we were calculating the total number of numbers, how it's going to affect the sum, what were the repetitions here, remove those, what were the cases that we were excluding, what were the cases that we were supposed to remove. Just do the same thing here and you'll have your answer. Now, the next type of questions that we're going to cover today is exponent of prime. Okay, exponent of prime, that means in a large number we need to find what is going to be the power of a given prime number in the prime factorization of that big number. So, for example, let's say we have n factorial. Okay, we have n factorial, a given number n, it can be anything, and we need to find for a given prime number p, what is going to be the power of this prime number p when we write the entire prime factorization of n factorial, not n factorial. So bache, let's understand this using an example first. We have 10 factorial. Okay, so here we have 10 into 9 into 8 into 7 up to 1. We need to find the power of 2. Okay, so we write the prime factorization. What all prime numbers will be here? There will be 2, 3, 5 and 7, right? Because 1 to 10 all the numbers are here, so all the prime numbers up to 10 will be here. 11 won't be here because 11 is not smaller than 10, so 11 is not included here. All prime numbers up to 10 will be here. Now, let's say we need to find this alpha. We write the prime factorization like this and we need to find what this alpha is, or this beta, or the gamma, or the delta. So let's first take a look at 2. Okay, how many 2's will be here? Where are we getting these 2's from? We're getting 1, 2 from here. We are actually going to get 1, 2 from all the even numbers, right? Every even number will at least give 1, 2. I have 1, 2. Every even number has a 2. I'll give my 2 to you. So, every even number is giving 1, 2. So, we will write, but I hope you know what this symbol is. This is greatest integer. This means if we are writing 10 by 2, greatest integer, that means the greatest integer, the largest integer, that is either equal to this quantity between the brackets or just smaller. Okay, the largest integer possible, which is either equal to or smaller than this. For example, if we have greatest integer 7.7, that is 7. Greatest integer 9, that is 9. Either equal to or just less than that quantity. Coming back here, so that means however, like the total number of even numbers here. What is the total number of even numbers? We divide this by 2 and take the greatest integer, because it will be an integer, right? It will be a natural number. How many even numbers are here? That will not be a fraction. There will be a fixed integral answer to this question. So that means we have here 1, 2, 3, 4, 5. Where did we get this 5 from? Because 10 divided by 2 is 5. Now, that's not all the 2's that we are going to get. We're also getting another 2 from all the multiples of 4, right? All multiples of 4 will have one extra 2 to give. When this 2 gave its 2, now only 1 was remaining. When 6 gave away its 2, only 3 was remaining. But when 4 gave away its 2, there was still an even number remaining. It was still 2. It could still give one more 2. So, every multiple of 4 will give its 2. So, now how many multiples of 4 are here? 10 divided by 4, which is 2.5. Now, of course, there are not 2.5 multiples. The greatest integer, the integer just smaller than 2.5, 2. 4 and 8. So 10 divided by 2 square, 4, and its greatest integer, so 2. Now, is that all? No, because even though when it gave away its second 2, now there was only 1 remaining. But when 8 gave away 2 of its 2's, there's still 1 2 remaining. It can still give 1 2. So now there will be, that means there will be 1 additional 2 in the prime factorization. Where is this 1 coming from? How many multiples of 8 are here? Same as before, 10 divided by 8 or 2 cube and its greatest integer. 10 divided by 8 is 1.25 and we just take its greatest integer. Only 1 is the answer. So 5 plus 2 plus 1, that is 8. Okay, so that is how we can calculate any prime numbers exponent in any numbers factorial. We just keep looking at this until the prime number raised to power 4 became greater than 10. We are not checking 2 raised to power 4. Why we are not checking 2 raised to power 4? Because 2 raised to power 4 is greater than 10. That means anything after this will be 0, right? 10 divided by 16 is 0 point something, greatest integer 0. 10 divided by 32, 0 point something, greatest integer 0. So we are not counting any further. Everything else after this will be 0. So we will stop here. Alright. So the general formula becomes n by p, greatest integer, then n by p square, greatest integer, n by p cube, greatest integer, n by pk, until it is non-zero. As soon as you get a 0, you stop there. Okay. So as soon as the p raised to power k becomes greater than n, you stop there. Alright. So a quick application. What will be the exponent of 3 in 10 factorial? Very good. So E3 in 10 factorial will be 10 by 3 plus 10 by 3 square. Now the next 27 is greater than 10. So we'll stop here. So 3 plus 1, that is 4. Right? Clear? Now try this one. Exponent of 7 in 100 C50. There's no factorial here, so we can directly not use that formula, but maybe we can use this application. Carefully, logically think about it. I'm still not seeing a correct answer in the options. Still keep trying, bache. Yes, 0 is the correct answer. Very good. So let's take a look. What was the formula? N by p square, n by p cube for n factorial, right? So E7 in 100 factorial is 100 by 7 greatest integer plus 100 by 7 square greatest integer, and then 7 cube is 343, which is greater than 100, so we stop right here. Okay, so 100 by 7, that is 14 point something, because 7 into 14 is 98, so we get 14 here, and 49 into 2 is 98, so 2 here. So 16 in 100 factorial. Now what is 100C50? 100C50 is 100 factorial divided by 50 factorial, 50 factorial. The exponent of 7 in 100 factorial is 16. That means 100 factorial is equal to some k1 into 7 raised to power 16. Correct? Similarly, we'll count for 50 factorial because we also need that here. So 50 factorial, by same logic, 50 by 7 plus 50 by 7 square, and we stop here. So 50 by 7, 7 plus 50 by 49, 1, so 8. That means 50 factorial is k2 times 7 raised to power 8. This k1 and k2 does not have any 7. It's some other prime numbers and some other prime factorization, but 7's exponent, because we only care about 7's exponent, so it is 7 raised to power 16 and 7 raised to power 8. Now coming back here, that means this becomes 100C50 becomes k1 into 7 raised to power 16 divided by k2 into 7 raised to power 8 whole square. So we are going to ignore k1 by k2 square. These do not have any 7's. This becomes 7 raised to power 16 minus this. Just using exponent rules. So 16 minus 16, 0. That means there will be no 7 in the prime factorization of 100C50. So k1 by k2 square into 7 raised to power 0. So there is no 7 in this part, there is no remaining 7 in the other part. So the correct answer is 0. Okay. So very logically we have to use the formula. Now, how many zeros are here at the end of 108 factorial? That means, how many zeros? What does that mean? Exponent of 10. Okay, exponent of 10. But 10 is not a prime number. Remember, the formula was for prime number. That method only worked for prime numbers. So what is 10? 10 is 2 into 5. That means there will be some 2's and some 5's. We are going to take same number of 2's and 5's out of those, and we are going to get a 10 from each pair of 2 and 5. Now how many pairs can we make? How many pairs can we make? The minimum number out of those two, the smaller number, we will have clearly, because 2 is smaller, we'll have more 2's, 5 is larger, so we'll have less 5's. So that means, remember, that is very important. We'll have more 5's and less 2's, so we have to only check exponent of 5. Exponent of 2 will always be greater than 5's exponent, because 2 is smaller, there will be more 2's there, right? But exponent of 5 will be smaller, so that is the maximum pairs we can get. More than that, it's impossible to make, right? We can only make those many pairs of 2 and 5. So that is our problem. Now we know the answer. 108 by 5 plus 108 by 5 square, and then 5 cube is 125, that is larger than 108, so we stop here. So this is 21, this is 4, so the answer is 25. Okay, so whenever we have to find exponent of a composite number, we are going to split it into the prime factors, and we'll see how many pairs, how many combinations we can make depending on what the larger number there is. Okay. Now, the last category for today. I think the first two were fairly easy. Even this is easy as soon as you understand how to approach such problems. So, The third category for today, the third type of questions, the last type of questions that we are going to understand today, they seem to be very tricky, but it is actually very easy once you learn how to actually solve them. So what is the type of question? What are the questions that we are looking at? We are looking at selecting non-adjacent, non-consecutive objects. We are given some objects, they are placed in a certain order. We have to pick some out of them. Okay, we are given n objects, we have to take r out of them, NCR. That was the original thing. Now there's a condition there that we cannot pick a consecutive, any two adjacent objects. If we have picked the second number, that means we cannot pick the object on the first number or on the third number, right? That is our problem. So the simplest way to do it is by assigning them 0 or 1. Okay, if we take them, we give them a 0, we don't take them, we give them a 1, something like this. Just any order, you can give 0 to one kind and 1 to other. So we call it binary equivalent, right? In binary we have zeros and ones and that's it, right? If it is true, we give it 1. If it is false, we give it 0. That is what binary is. The same way we are going to look at the problem here. So for example, let's look at an example. It will be very clear in just a minute. The question is, how many ways can 4 trees be cut from 10 trees in a row such that no 2 trees cut are consecutive? Okay, it is not possible that we cut this and this. These are consecutive, we cannot do this. So that means we have to select 4 trees out of these 10 such that no 2 out of those 4 are adjacent to each other. Another problem, another way of looking at this problem is, we are assigning 0 to the tree which is being cut and 1 to the tree that is still going to be there. Okay, so that means we are going to have 6 ones and 4 zeros. Right? For example, let's take a look at this arrangement of ones and zeros. We have this 0, this 0, this 0, this 0. We can see that no 2 zeros are adjacent to each other. We have 4 zeros and 6 ones. So we will cut these 4 trees. Or if we take a look at this one, we again have 4 zeros, no 2 zeros are adjacent to each other, and we cut this, this, this and this. So every unique arrangement of ones and zeros will give us a unique answer for our problem, unique selection. Okay, so now it's a very simple problem. It's just the gap method, right? We first arrange the ones. How many arrangements? In this case, because they are identical, there is only one arrangement, right? We have 6 ones, we just arrange them 1, 2, 3, 4, 5, 6. We place these 6 ones. There's only one possibility of doing this. Now we have to insert zeros between these gaps. How many gaps do we have? 6, 1, so 7 gaps. 6 plus 1, 7 gaps, and we have to select 4 gaps out of these 7. So 7C 4, and that is your final answer. So instead of selecting 4 out of 10 and looking at the cases where they could be adjacent, we can simply do it in the opposite way. We make arrangements of ones and zeros. Okay, let's take a look at another application of the same thing. An engineer has to visit a factory for exactly 4 days during a period of 15 days. Okay, every month within the first 15 days, the engineer has to visit 4 times on 4 days, and it is mandatory that no 2 visits take place on consecutive days. Basically, out of those 15 days, the engineer has to select 4 days, and such that no 2 out of those 4 days are consecutive, are adjacent to each other in that arrangement. Number of all possible ways that they can do it is, we place all the ones first. How many ones? 4 zeros and the remaining 11 ones, right? We place all the 11 ones first, only one possible arrangement to do that, and then 12 gaps, 11 plus 1, 12 gaps. Out of those 12 gaps, we have to select 4, and that is your final answer. Alright? So, very easily you can do it. Just you have to transform the problem. You have to take a look at the problem from another angle, and then it becomes super easy. Okay? Clear to everyone? Alright. Now let's take a look at this problem where it's a circular arrangement. Now instead of a linear arrangement, we have 10 people sitting around a circle. And they are people, they are not identical, they are 10 different people sitting around a table. We don't have to find the arrangements, right? They are already sitting here. There are 10 people around here, they are already sitting. We just have to pick 3 out of these such that no 2 out of those 3 are sitting adjacent to each other. If we pick P1, then we cannot pick P2 or P10. Okay? So, just try it once and then we'll discuss the solution. Yes, 50 is the correct answer. Yes. So, 50 is the correct answer, bache. 35, I know. If you, let's see. What if, again, we have the same thing, right? We have to arrange zeros and ones. How many zeros, how many ones? Let's say we are giving 0 to the people who are not going to be here anymore. The 3 people that we have to select. Okay. So, 3 zeros and 7 ones. If we just arrange these 7 ones and 3 zeros around a circle, then you might say that we first place all the ones and then out of the remaining gaps, 7 gaps, because it's a circular arrangement, so out of the remaining 7 gaps, we will select 3. And this is 35. But this is wrong. Why is this wrong? If we placed 1, 1, 1, 1, 1, 1. We arranged in a certain order 1. Now once there was only one order for the 7 ones, right? Now you're inserting zeros here. Let's say I want to insert a 0 here. How can I do it? I already placed the 1. Or if you're saying, ma'am, just shift it by 1, then there are a lot of cases for each of them. Right? If you're shifting, you will have to consider, can we shift it? How do we shift it? So that is why we're not counting all the cases. So bache, the student who got the answer as 35, that is why it is not correct, because we have to see the placement here is not identical because they are different, distinct 10 people. So how do we actually calculate? One way of looking at this is we fixed one person, okay? This one, the one sitting in the, we number all the people, and the first person, we take 2 cases for this first person. Case 1 is, T1 is not selected. Okay, that means we are giving this P1 a 1. Now it's a linear problem, right? Whichever arrangement we have of the remaining 6 ones and 3 zeros, the linear arrangement, we just place it here, right? As soon as we fix the answer for this one, now we just arrange the remaining 6 ones and 3 zeros, and we will have a unique arrangement for this particular case. So what will be the arrangement? We arrange the 6 ones, that's only one possibilities, and then 7C3. So that is now 35. Now let's take a look at case 2. When P1 is not selected. Okay, that is P1 gets a 0. Now it's not the same as arranging 7 ones and 2 zeros. If we arrange 7 ones and 2 zeros, it is possible that we get a 0 here. That is not possible. So that means we have to impose the condition that adjacent to this P1, P2 and P10 cannot be selected, which means P10 will be a 1, P2 will also be a 1. Because these two cannot be selected. As soon as we selected P1, we made sure that P2 and P10 cannot be selected. Now, for the remaining P3 to P9, this is a linear arrangement. Now we arrange these in any way we want and we will get a unique answer. So now how many ones and zeros do we have? We took 2 ones, so we have 5 ones remaining. We took 1 0, so we have 2 zeros remaining. So we place the 5 ones, out of the 6 gaps we place 2 zeros. So 6C2, that is 6 into 5 by 2, that is 15. And now only these two cases are possible. Either P1 is selected or P1 is not selected, right? And for each of these cases, we counted the total number of possibilities. So 35 plus 15, the answer is 50. Okay? Yes, Vichit, this is very helpful for JEE as well. Okay, so that is how we can actually apply all the same things in different scenarios. Just be very careful. Can we apply this? Are we sure we are counting all the possible cases? Are we sure we're not missing any case? Are we sure we're not counting any case? Again, I keep repeating this in every class, but that is all what this chapter is about. You just have to make sure you're counting all the cases and that's it. It's just different ways, different methods of making sure that you're counting all the cases. Okay, so in today we are going to just stop the class here. Yes, we ended the class earlier today, but we did learn a lot of new things today, a bunch of different methods of solving these things. In the next class, we are going to do inclusion-exclusion principle. We are going to start with inclusion-exclusion and then we're going to look at one of its applications, derangements, where none of the objects can be in their original place. So we're going to see all of that. Again, very logical, just have to understand. So we will actually look at this problem again from a different angle and we're going to reach the same answer. Of course, if the method is correct, you're going to get the same answer, but we're going to start with inclusion-exclusion principle in the next class and we are going to see how this is also an application of that principle, how we could have actually used that method to solve this question. Okay, so yes, I can see the answers. You're good, you're right. But before explaining the theory how we can actually do it, I don't want to get into it. So in the next class, we will study what that is, what is inclusion exclusion, and how to actually apply it in the problems that we have already seen, as well as in the problems that cannot be solved in any other way. Okay, so I will see you next time. Make sure you revise everything you learned today, even if you felt it was easy. Still, it's a very good practice to revise. You have to revise regularly. You have to just, after any class ends, you have to make sure that you go through it again so that you never forget anything you learned in the class. ठीक है, चलिए, आई विल सी यू इन द नेक्स्ट टाइम, बाय।